यूट्यूब लिंक शेयर करना है, सर को भेज दीजिए, सर को भेज दीजिए, सर भेज देंगे। Avasti sir?
Yes.
We are sharing it with you on your WhatsApp number.
Sure. I'm waiting for it.
Yes, sir. Anuk sir is in fact giving it to you on your phone number.
Yeah, I will prefer WhatsApp number.
Avasti sir?
Yes.
We are sharing it with you on your WhatsApp number.
Sure. I'm waiting for it.
Sir, Anuk sir is in fact giving it to you on your phone number.
Okay. Yeah, I will prefer WhatsApp number.
Avasti sir, I will request you to please mute the YouTube link because the double voice is coming from that. Sir, Anuk sir is in fact giving it to you on your phone number.
Okay. Yeah, I will prefer WhatsApp number. Hello.
Ram sir, can we proceed now?
Just I just received it. Just a minute.
Okay, sir. No problem. Yes, sir. Yes, sir. Ram sir, can we proceed now?
Hello.
राम सर,
हाँ
सर आप प्लीज यूट्यूब प्लीज बंद कर लीजिएगा क्योंकि उसी का भी आवाज जो है बार बार आ रहा है।
कैसे मैं बंद करूंगा यूट्यूब? वो मुझे समझ में नहीं आ रहा है।
आपने सर कोई दूसरे विंडो में यूट्यूब तो नहीं खोल रखा है सर?
नहीं मैंने नहीं खोला हुआ है।
तब ठीक है सर, देन इट्स ओके।
Okay, so should we start, right? Okay, sorry audience for this delay. Manish is sharing the screen and I'm speaking over phone. There was too much trouble. So coming to the presentation, can you make it full screen or is it full screen? So what is this title about? What is this title all about? So I will crack it down, alphabet and grammar of nature. So from this alphabet and grammar of nature, I want to really address the question that how nature actually works. Is it so many dramatical ways we see in this world? So many phenomena, so many distinct things happening all around millions, billions of the stars, almost all of different kinds, millions of the species in this world, millions of the viruses, so to say, thousands of the molecules and hundreds of the atoms, or there are just few simple rules which mysteriously give rise to these composite effects that we eventually see the world in so many different ways. The list I made from stars to atoms, you might have observed that the list is actually decreasing in the numbers. And from perception to comprehension is about what would happen if a naive person, first person on the planet who do not have any tools, nothing too much, but is full-fledged human being, how he will start perceiving the nature around him, how he will start observing things, how he will start reacting to the environment. From there to the current time when we have modern tools and technologies to really dig down deeper into the nature of physics. So how this journey, I mean, I will try to take you through partial journey of this development um, in this discussion. Next slide. Hello. Manish, could you please move to next slide?
Hello, sir. Actually, we are sharing PDF, so we have to scroll down.
Yeah,
So
yeah.
Yes, sir. So I have scrolled down to the next slide.
You can make it into presentation form and then scroll.
So this is the next slide. I have to, I think.
It is not updating here.
But from my side, sir, it has been updated. Sir, did you get the current slide?
No, I didn't get. Is rest of the audience getting the next slide? If that is working, then also I can continue.
Okay. One second, sir. Then we are again trying to reshare it. I am just stopping this share screen. इसमें तो सर इक्वेशन नहीं आएगा Hello, sir.
Yes.
Hello, sir.
Yes.
Hello, sir. Sir, we are having problem in a PDF sharing, sir. So let's go
Okay.
with PPT, sir. No problem. We can share the formulas later on, sir.
Okay.
Extremely sorry, sir.
Okay.
Should not be a big problem, sir. For the audience also, sir. I hope.
Yeah. So go to the second slide.
Sir. This is
Yeah.
fine, sir. This.
Yeah. Yeah, so 5 sensory organs. We have these 5 sensory organs to touch, smell, hear, taste, and see. And what these organs are actually the tools. Not to the next slide, please. Please to the previous slide. Yeah. So these 5 sensory organs are to taste, hear, uh, smell, touch, and see. But what they actually are fundamentally doing uh, with the help of brain. Next slide, please. Is basically this touch, this skin is actually sensing the thermal and texture. Sometimes you touch a cloth and you see a cloth and you are not able to guess the texture and the quality of cloth. But if you touch it, then you know better. Similarly, the nose and the tongue are sensor for chemical composition. The material you have near you is some particles are getting spread in the air and they are reaching to your nose, and then you are able to really smell them. It gives you the information about the chemical composition of the material. And similarly, chemical composition by tasting it. Ears are actually giving the information about the dynamics in the environment. Basically, if you environment could be air or the water or any other environment. There is directional information also. What eyes are doing actually giving you the geometrical information, color, in addition to, on top of the vague quantities like seeing and hearing and tasting. So these organs are connected with the brain, which is your logical unit, which process the information you collect from these organs. So these organs are kind of detectors of your detectors. So if you have only one organ and use your brain, there is very likelihood that you can miss the complete picture uh, uh, of the nature. So if you go to the next slide, you can see here 6 gentlemen who are not able to see are trying to detect the elephant, and they have their own interpretation depending on what they actually have touched. So if you are using only one organ, sensory organ, then there is likelihood that you can miss the essential nature. Whenever you are walking, then what you are actually doing is using your eyes. You are also using your ears and your skin to avoid places not where to go, where not to go. And this way, actually, all these 5 organs are collectively working together for you to the survival. So next slide, please. So these 5 sensory organs are kind of most important instruments for your survivals. There are arguments that there are more than 5 more than 5 sensory organs, but we can, for the time being, avoid going into discussion of that. Even these most sophisticated organs are not skilled enough to give you the information about the nature most precisely. What is the benefit of having these tools with you is that they are inbuilt. They are inbuilt tools, and since we have been using them for the millions of the years from the starting of the life on Earth, we have been using them, and we So we have developed genetically encoded information that these are the things you do. So whatever you actually taste good, almost everybody feels that it is good, and whatever you smell is bad, almost everybody feels that that smell is really bad. And that is actually has happened through the process of evolution of humankind, that we are able to have the similar feeling about nature. So but there are the deficiencies in these five sensory organs, and those deficiencies are that the precision is really very poor. For one person, a sweet may be really very good, but for someone else, it may not be that good. Somebody may like drinking milk, somebody may not like drinking milk. There is no clear cut precise process of sharing the information about of any uh, physical condition, physical property of the external universe. You cannot really, you can say that it's really very hot, but you cannot say how much hot. So there are problems in precision of the detection, and the problem in sharing the information. So accuracy and commutability are these two issues with our sensory organs. Therefore, we require external tools and technologies and the language to share this the information collected by those tools. And these tools make the require the unit system for corresponding to certain property you want to measure, and then that unit has to be supplemented with the value. Value means relevance, relation. So even if you touch something, you say that is not that much hot. You say that something else is really very hot, and something else is very hot. So this is the relation we make depending on the temperature of our skin. So similarly, we need to have a value system, and that unit and value system makes our scale. So to the next page. Yeah. So first scale, which goes beyond sensory organs. You can take a simple meter scale, and distance measurement are perhaps the most simplistic to perceive, to understand. And therefore I think, I suppose that meter scale or some sort of a scale of measurement of the distance would have been the first discovery of a scaling system or of any instrument. uh, so this scale, it's not really necessary. What are these markings on this scale? Uniform, you do a uniform marking. It's not necessary that whether what you mark on it, how you mark on it. The important thing is that universality of that marking, that you have marked with some spacing a scale, someone else have marked with a different level, then these two things should be interconvertible. If they are not interconvertible, then then there is a problem. Or better, it would be that everybody follows the same scale system. So this marking requires, I mean, if there are markings only on a scale of meter size, then after a time you will lose the track. So at places you require the numbers to put. So counting has to be done. And counting, we can train our brain. Human can train its brain to really keep track of the history. So in addition to these marks in the meter scale, there are numbers placed so that you don't have to go back and count again whenever you want to count. Now this accuracy of this meter scale depends on the universality of the scale up to good extent, that if it's universal, then this is benchmarked scale. So next slide, please. So considering about the meter scale only, you have to define this scale. So 1 meter was first in the very beginning, of 18th and at the end of 18th century was defined the distance, some fraction of distance between 2 points in the on Earth. But this is very ugly definition. You cannot keep track of it. I mean, you will have to all the time take the thread from first point to second point and then divide into equal pieces, and it's a hell lot of work. Therefore, people came up with a different definition. They placed a prototype meter bar at some place under this or that environmental condition. This or that environmental condition is required because if the environment changes, the temperature changes, then this bar will melt. If it is a metal bar, it will melt and will increase in the size. And then your definition of meter scale is again is in trouble. So either you define that these are the environmental condition, or you come up with a better definition. And then people came in 1960 came up with the certain number of wavelengths of krypton, defining as a meter scale. And then when measurement of time actually became more and more accurate with the development of quantum measurements, and with this idea that velocity of light in vacuum is frame independent, inertial frame independent, people started defining the meter scale in terms of velocity of light and second. Next slide, please. So we require numbers. Numbers we have been knowing for long, but to have really good understanding about numbers, how they are defined, how they are there, what are the consistency conditions. We have been using numbers for long, like in thousands of the years, but we have not been using them for millions years before that. So it's not easy to perceive them. And a real good axiomatic representation came very late in the time of Peano, who gave axioms that you start with a number. And these axioms are about natural numbers I'm talking. So you start with a number, you have to start somewhere. And then if you define a certain number, arbitrary number n, then its successor is also natural number. If your n is a natural number, then its successor is also natural number. And your first initial point, you call it 0. First initial point, you call it 0. It is not successor of any other natural number, right? And similarly, two successors, if two successors are same, then the two natural numbers of which these successors belong to should also be the same, right? So means there is only one successor of one natural number. There are not more than one successor of one natural number, or there are not one successor of multiple numbers. So these kind of exclusions have to be made, and then there is a condition of mathematical induction, that your first axiom is true, then if nth axiom is true, then n plus 1th means successive axiom is also true. And this is the way we define the natural numbers. And from these natural numbers, we can come up with, extending these natural numbers, we can come up with the fractional, rational, irrational, and real and complex numbers also. And then complex functions and all the development in mathematics has happened over the 400-500 years, uh, uh, can be can be discussed in several classes courses of the mathematics. In the right hand side, I have shown a few devices, uh, Vernier calipers and screw gauge, which measure the distance, these thermometers, which measures the temperature, this weight meter, which measures the weight, and voltmeter, clock, and there is a digital meter also in the down. So what is similarity in these initial level of, I mean, these developments are really recent compared to the human history. What are these things? They are actually numbers placed on a scale. So this thermometer is measuring a distance in a sense, because our brain is more trained to see the distance, to see the separation between 2 points. And by saying that, I'm actually emphasizing on the development of one particular sensory organ, eye. More eye is more advanced compared to other sensory organs. If you want to know the temperature, how you would like to hear all the time. If you want to know the information collected somewhere, you want to read a book, you want to read a book, I mean, you use your eyes. You cannot use your ears to read a book, I mean, to know a book. You can hear, of course, you can devise some instrument, you can devise which will tell you all the time that what is the temperature. But if there is too much information, and if you want only some part of that information, you cannot all the time use your ear or your skin. You cannot touch the voltage. You cannot touch it and know it. But with the eye supplemented with the brain, which can process the numbers, you can measure the voltage. And then in a meter scale, in some simple scale, voltmeter scale, you can easily see what is the voltage between two plates, or between anything. And similarly, weight. So this eyes got importance over the other sensory organs. Therefore we use them most of the times. Even if we didn't have other sensory or other organs, we had eyes only. And these tools, external tools, we could be very well surviving this earth without much trouble. Next page, please. Yeah, so eye and brain. So this space doesn't have much information. Eyes and brain combined, supplemented with these tools, does the job. You really do not have to place a scale. You just, if you have a meter which counts the number, if you know that what this meter is counting, you will have to have different meters of always, of course. But if you know that this is voltmeter and this is counting 24.3, then definitely you are measuring voltage. If it is current meter, then ammeter, then you are measuring 24.3 unit of current, whatever unit it is. If you know that, then you don't really need the scale. You can work with the number only. Next slide, please. So we want to, there's a big question is that how does the brain analyze the information passed by the body organs? So this is a big question. Things are still being studied. And in previous couple of slides, actually, we tried to understand that there's some information is actually being passed from these detectors of the human body to the brain. And there is a whole lot of study about the neurons, connection of neurons with the brain, and these There is nowadays a study of neural network, and this artificial intelligence also is going on. So brain, we are trying to mimic the behavior of brain, how it processes the information. Hopefully we will eventually, at the end of our struggle, we will be able to understand how this brain processes the information. So next question we want to address is this world perceived by the sensory organs all? Is this all? So, well, yeah, I'm including the voltage, which we cannot see, but if we touch the voltage difference, we will definitely get shock, and then we will know that there is a voltage difference. So including that, whatever the world we perceive by sensory organs, is this all? No, today we know that there is a microscopic world, whole lot of microscopic world, microorganisms, cells, molecules, atoms, nucleons, electrons, quarks, and all kinds of particles at the microscopic level. And then there are objects which are not easily reachable, like even including the solar system. We cannot see everything using our naked eye. We require sophisticated telescopes to see distant planets. And then there are clusters of star galaxies, cluster of galaxies. Well, you can claim that you can see them, so you know about them, but you actually, the thing is that what is going inside that a star is a completely different world. Whole lot of physical processes are going inside of a star. You are just seeing part of it. So there are stars, I mean, there's cold stars and cold galaxies which do not emit visible light. Then how you will know about them, how you will perceive about them, how you will comprehend about them, that what they are actually doing. After this, actually, I had a video is named A Scale of Physics. People can go on YouTube and try to find out a scale of physics. And there, what in a short video I tried to show is that size of universe is around 10 power 27. We are about of the order of 1 meter, and Planck length is of the order of 10 power minus 35 meter. So physics is so vast that it goes from 10 power minus 35 meter scale to 10 power 27 meter scales. And if you scale this energy in terms of energy, it goes from milli electron volt to 10 to power 19 electron volt energy scale. So this much variation we see in the physics. So this much variation we see in physics. And that's why you have so many books on different topics of the physics. So important thing is that in this universe is that whether we see the static universe or we really want to do some predictions about the future of any system. So the dynamics or the evolution of the system is really necessary. And how does it help? We do some observation. If we have only observation, we will not be able to really predict what is going to happen in future. You can say, I mean, if you have something to eat, you eat it now, otherwise in 5 minutes it may spoil. Oh, well, you can say that, okay, I know it will not spoil for a day. But to scale the same thing, whether how your laptop battery is responding, how it will evolve, how your CPU will process, that is important. And that you do not know unless you have all the control over even at the atomic scale of the battery, that how it behaves, how it evolves, what is the dynamics. So to comprehend the evolution, we need to come up with the theories which verify the observations. That's not sufficient for a theory to survive. That theory may be right, may be wrong, may be hunch. But if that theory is able to predict something, and then you are able to observe that different thing also and verify it, then you can say that, okay, to the next level, my theory is actually more correct. So that way you develop a theory, predict it, and then there may arise new questions, and then you may have to address those new questions also. So development of the theory based on mathematical arguments keeps on evolving, and there may be day that we will end up with a uniform universal theory of everything, but that day may never come. Next slide, please. Yeah, so these equations actually are not very clear here, but I will try to explain in a little detail. So first thing for the...
Excuse me, sir. We will share the PDF with the participants. So
Okay.
it is okay.
It's
Yeah.
okay. Yeah, so this first revolution, I mean, the study of science have been happening from the time of Euclid and Archimedes, like 2.5 thousand years back. But real development only started when calculus was developed. Though calculus was known to Indians from 12th century, but it was not used to explain the physical phenomena. It was Newton, excellence of Newton, who gave it a equation for the dynamics of the system, of a system. So if you see, these first two equations are not very important. They are general differential equations of multiple variable pre-parameters. And the second one is ordinary differential equation of order n. And in the right hand side, if you see a c, which is a constant, you can make it 0 without losing any generality. So this third equation is Newton's law of dynamics, which says that in the left hand side, I will take the rate of change of position. So there's a d square x by dt square, rate of change of position. Multiplied with mass, I will call this force. So this was the first mathematical way of defining the force, defining dynamics. And this force in the right hand side can be anything. It can be F is equal to ma. And don't get confused that in the left hand side also you have ma. No, in the left hand side you don't have ma. In the left hand side you have m d square x by dt square, which is variance of position. And in the right hand side you have acceleration, constant acceleration. And in place of force, you had to have constant acceleration. You need to make a force, you need to multiply with a mass. And that mass cannot be any different from the mass of dynamics of which you are studying. So therefore, this F is equal to ma. Second force I have written is the universal gravitation, Newton's gravitation, G m by r square, which says that a smaller mass at position x is experiencing the interaction or attraction due to capital mass positioned at x naught. And the third kind of interaction is quite similar to the gravitational law, which is two charges divided by distance separation between them. But this is not quite the same, because in the gravitational law you have mass. In the left hand side you have mass, in the right hand side you have masses. But in this one you have, in the left hand side you have mass and you have different property charge in the right hand side. So if you just place this F in this differential equation, dynamical equation, there is nothing wrong about the equation. You can solve it. but physically it will be incorrect. And the reason is that associated with all the electric fields, there is a magnetic field whenever a charged particle is moving. Okay, so this force in the right hand side of differential equation form contains time dependence also. It can contain position, position prime, position triple prime, double derivative I have taken to the left, and any arbitrary higher order of differentiation it can take. But the problem is that we cannot analytically or we are not very good at perceiving or comprehending about the higher order differentiation. So if there are higher order derivatives of position in the right hand side, better they should be smaller, so that we could handle them perturbatively. And I will at the end of the talk also claim that perturbation analysis is the most fundamental analysis, is the only way you can handle complicated problems. So going to the next page. So if I take just the first force, md square x by dt square is equal to ma, you can write the laws of motion, Newton's laws of motion, velocity v is equal to u plus at, and then s, and so on. Suppose your a is non-zero and you take time going to the infinity, then your velocity will go to the infinity. But what actually happens is that in laboratory tabletop experiments, you can see that it doesn't appear to be happening. You just give a million electron volt of potential difference to an electron. In a meter, it will take the half of the velocity of light. And if you double it, the potential difference, the velocity of light, velocity of electron doesn't become velocity of light. It increases by a slight amount. And then you keep on increasing the potential difference. It never reaches. Even these protons and electrons at LEP and LSC are running very close to the speed of light, very fast, but they are never reaching to the speed of light. And therefore, these equations themselves have fundamental problem of being defined for all time. Okay, though these equations are invariant under Galilean transformation, but they have this problem. On the other hand, electrodynamics was independently being developed as a classical theory of fields that was inconsistent with the Galilean transformation, but was giving the correct results at all time scales. Therefore, we had to either decide whether we abandon the electrodynamics equation and write new equations consistent with the Galilean transformation, which people tried and failed because they were unable to predict the observations, or you change the Newton's dynamic equation so that it is consistent with the higher speed. And there comes the special theory of relativity, which supplements the dynamics, Newtonian dynamics, which gives the Newtonian dynamics at the lower energy, lower velocities, and is consistent with the symmetry and physical requirements of being at higher velocities. And what change actually happens is that now your momentum is actually gamma mv, where gamma is a Lorentz factor, and your transformation, new transformations large are called Lorentz transformation. Now this way, if you calculate the velocity of any particle, it never goes beyond the terminal velocity, which accidentally is velocity of light in vacuum, which is accidentally, not necessarily. There could be another different terminal velocity. Accidentally, it is velocity of light in vacuum. So next page, please. Yeah, so Newton's gravitational dynamics, in the right hand side, you just place another force, gmm by r square. There is a negative sign because this force is attractive. And if you study for two body system, then you will see two ellipses, and these two bodies are revolving around each other. This theory is action at a distance, so very good candidate for field description. And in fact, gravity was not developed for long as a field theory, but electrodynamics had from the very beginning of Maxwell. Maxwell's wrote the equations of electromagnetic wave. From then, it has been treated as a wave theory, field theory. This equation again has another problem, that information is running very fast. So you place in the right hand side, there is no time information. So you place masses at different location, and then immediately the force is felt by different the another mass. So this has this problem also, that this information is running with infinite velocity. So that should not be happening, and for that not to happen, we need to introduce to extend this theory of gravitation. The other figure is three-body dynamics, which we cannot analytically solve precisely, but using numerical method, computer, you can write a very simple computer code to simulate the dynamics of three-body or any n-body system. This equation is consistent only in the limits when v is much less than c, which is almost always the case, as you can see in case of solar, sun and earth system also. This is very accurate. Next page. But this theory actually fails to explain the perihelion of Mercury. And then there comes the general theory of relativity, where the concept is that due to presence of a massive body in the space itself gets curved. Properties of space changes. And then the Euclidean property of space, which is ds square is equal to sum over dxi square, is
Sir.
no more valid. Yes.
Excuse me, sir. Sir, we have successfully converted the PDF into presentation mode. So we can share it now. So the equation are fine now. Can you share it?
Yeah, okay, you can share. Will I get 20 minutes more?
Yeah, of course.
Okay, good.
Let me share, sir.
Sure.
Okay, sir. I'm sharing now. So let me check first, sir. Let me check. Check first. Sir, now fine. Equation is fine now.
Okay, great.
Yeah, na?
So next page.
Okay.
Yeah.
This one, sir.
Yeah, this one.
It's clear now, sir. Huh?
Yeah, right.
Yeah.
It's
Okay.
good.
Okay.
So this, with the introduction of general theory of relativity, Euclidean geometry in the left-hand side of this arrow gets replaced with the right-hand side of the arrow, where your metric is no more 1, 1, 1, and distance ds square is the distance square measurement. And this theory itself is quite complicated and requires a couple of courses to cover to reach this equation, which I have written at the bottom, in which left hand side is actually purely geometrical, and in the right hand side is actually purely materialistic. means matter property. So right hand side is called actually stress energy tensor. And this was able to explain the perihelion of Mercury, and so far have been a consistent theory. Using this general theory of relativity, we have set up the global positioning system, which works only because general theory of relativity is correct. Next page, please. Yeah, so what I was talking about the electrodynamics is that it's not just the q by r square you place in the right hand side. You require something additional, and that additional term is actually q v cross b, because everywhere there is electric field. For a moving charge particle, there is a magnetic field. In one frame of reference where you are having purely electric field, if you change your frame of reference, you will get the magnetic field. So they are coupled with each other, and there is no way to escape. So this right hand side is called actually Lorentz force, and left hand side, of course, we know. So relativistic correction, if you do in the left hand side, we have dp by dt, and t gets replaced by gamma mv, and in the right hand side we get Liénard-Wittert correction to the moving charge. And this Liénard-Wittert correction you will you can see find in Griffith's book or Panofsky-Phillips book. Panofsky-Phillips book is good. Its expression is quite big, so that's why I have not written it here. What is beauty about this electrodynamics is that there are so many types of atoms, molecules, and materials, superconductors, nanotubes, graphenes, and there are on the other hand, existence of Earth, stars, and galaxies. Why do they really exist? And a whole lot of electronics, development of electronics starting from triode, diode, tetrode to the modern computer, supercomputer. And then there are so many atomic effects: Raman, Ozek, Compton, photoelectric, tunneling, quantum tunneling, laser and maser, and so many to count. There are so many processes. Like, I mean, why I'm standing on the Earth? It's because of electromagnetic interaction in one sense. I mean, of course, electromagnetic interaction is involved in it. And similarly, I mean, why a star survives, it doesn't collapse, why a galaxy survives, and so on. So many questions this electrodynamics actually handles, that this universe actually exists. Gravity would not let it exist if it were possible. So why it is happening with this electromagnetic charge is not just electromagnetic. It's about actually something more. Next page. And that something more is actually more intrinsic, is basically because the matter anything is composed of has different intrinsic properties. It doesn't have just mass only, it has now charge, and then there are other possible intrinsic properties. There is discreteness in the system. If something, there is a red light and there is a violet light, and if it were continuous, it would have been difficult to perceive, but it's not continuous. Things are discrete, and that's why we are able to see them different. Discrete, no, it's a one page previous to, I'm still in one page previous to this, but it's okay. I mean, you can screen this page also. So there is a discreteness, and there is exclusion between two things. I mean, they do not share the space. So this discreteness, exclusion, and intrinsic properties, I'm actually referring to the quantum phenomena, the quantum world. Next page, please. And in that one, actually, I'm emphasizing about the spin, discrete energy states, and and Pauli exclusion principle, which holds for fermionic particles. Fermionic particles are those particles which have fractional integer spin by 2. So what happened at the end of 19th century was that there was so much growth in spectroscopy, and this spectrum is actually emission spectrum of hydrogen atom. There are so many discrete lines, and they are forming certain kind of bands. They're forming a pattern. This had to be explained, and this could be explained. This could not be explained using classical energy, which is kinetic energy and potential energy and continuum energy, continuous energy spectrum. This would have been just a band, a complete band, not discrete lines. So Schrodinger's and other, so many people in the 21st quarter of the 20th century came up with the development of quantum mechanics. I have written one equation called Schrodinger wave equation, time dependent, and the other one is the time independent. When your Hamiltonian is actually time independent, you can separate out the time dependence part and take out the time independent equation. And this time independent equation, what you have from a spectroscopy is energies, energy levels. So in the right hand side, you could place E, and this Hamiltonian from classical mechanics we understand has to be a kinetic part and the potential part. So this kinetic part you can easily write del square by twice m, and the potential part you have to discover given the energy spectrum. So you can try to find out the potential. Fortunate thing was that we knew that from Rutherford scattering experiment and other experiment that whatever this atom is made of is actually a positive charge and a negative charge particle, which have some mass, of course. So if they are positive and negatively charged particle, definitely there would be a feeling electromagnetic interaction. So why not try with the electrostatic interaction? So this right hand side in the second equation, d E square upon 4 pi epsilon 0 r square is the Coulomb static interaction. You place it and you are precisely able to predict the this energy spectrum, given that you discretely write E is equal to h nu as Planck applied. So this will predict you the wavelengths, and these lines are actually corresponding to different wavelengths. So this Hamiltonian gets more and more scary. This itself is not easy to solve, but when we improve on the theory by introducing corrections, next slide please. And these corrections are like the following. Relativistic correction, spin orbit coupling, because though electron is moving quite non-relativistically, but still there are a relativistic correction. There is a spin, electron has a spin, and it is orbiting orbiting around the nucleus. So it has a spin orbit coupling. And there is a Lamb shift, which comes due to quantization of field. And then there are hyperfine structures due to the spin of the nucleus. And then there can be environmental effect. You might be placing your atom in external electromagnetic field, or any other such environmental condition. So if you introduce all these terms, your equation Hamiltonian will look quite ugly, and it will become difficult to calculate. But the preliminary first simplest Hamiltonian itself predicts to very good accuracy, this spectrum to very good accuracy. So you apply the correction need to requirement basis. Next page, please. But there are too many assumptions in this theory. I mean, in the theory I presented in the previous page. One thing is that it's a non-relativistic theory. Kinetic term is still p square by twice m. So it follows the fate of the classical theory of gravity. that we need to transform it to relativistic theory. And then there is no dynamical appearance of spin in the description, but observations say that particles have the spin. In the previous equation, wave function didn't require any particular information of the spin. And then the requirement of relativistic quantum mechanics made Klein-Gordon requirement of relativistically correct theory made Klein-Gordon to write equation box plus m square psi. I'm assuming that S cross and C are 1 here. So this is actually E square minus E square plus P square plus M square in operator form, written in the left-hand side to the psi. Psi is still a wave function. And then this theory actually gets in trouble because it gives a negative energy and negative probability density. So Dirac wanted to resolve these issues. He wrote a linear equation in energy, momentum, and mass. And that linear equation gets some matrix forms, gamma mu, and he gets positive probability density. But negative energy problem still survives. So he smartly tackles negative energy problems, giving the whole theory that all the negative energy states are filled with the electrons if you are giving the theory of electrons. And because of Pauli exclusion principle, no more electron can jump from higher energy, positive energy to negative energy. And therefore they survive as we see in this world. And if you impose energy greater than twice mc square, mass of m is mass of electron, then you can actually eject an electron, and there will be a vacancy in the Cia, that vacancy will actually act as a different particle moving with a different opposite energy, moving in the opposite direction with opposite spin, but same mass. And that he called is antiparticle. And antiparticles were actually discovered. So next please. So they discovered antiparticles, and with the replacement of q mu into p mu minus ea mu, which is like introducing electromagnetic interaction in your Hamiltonian, in non-relativistic regime, you get the spin automatically, or you can directly calculate the commutator of L plus half alpha tilde H, where alpha tilde is spin operator, and which gives eigenvalues half plus minus half. And this commutes, and therefore it says that this psi of Dirac has the information of spin in it. These wave functions are very peculiarly different from the classical treatment. In classical treatment, we never required the information about the particle or object we are studying. We just required mass of it. But now this wave function, we write, wave function is not the wave nature of the particle. People commonly misconfuse this wave function as the wave nature of the particle. No, this wave function is at actually the amplitude of the probability. So if this wave function mod square multiplied with dx will give you the probability of finding a particle in the range dx. So that way it is interpreted. But this wave function contains all the information about the system. Next page, please. So we talked about relativistic quantum mechanics. It has its own problems, that there are negative energy states. Well, negative energy states could be explained using whole theory in Dirac. Dirac was able to explain it in whole theory, but he couldn't. This explanation could not be implemented in the Klein-Gordon theory. On top of it, number of particles is conserved in relativistic quantum mechanics or quantum mechanics. What actually we observe is that there are various phenomena like electron positron going to muon, anti-muon. or muon decaying into electron, neutrino, electron, neutrino, and muon neutrino, or two electron colliding and giving 4 electrons. Such kind of processes are frequently happening depending on the energy scale you impose on your system. Next page, please. So you need to explain these things. And that explanation comes from quantum field theory, which is actually the combination of classical field theory, special relativity, and quantum mechanics. So there is a quantization, and there is a special relativistic treatment, means high velocity Lorentz invariance introduced in Lorentz invariance in the system, and the concept of classical field is introduced. And this quantum field theory is actually the crux of current today's particle with basic building block, basic language of the particle physics today. Particles now, the psi are now replaced by the field operators, and these particles are excitations of these fields. Interaction between different field excitations is local. Local means these point interactions. Interactions are point interaction. And these interactions are mediated by virtual particles, like you see in the right-hand side, electron and positron are colliding in the time running forward direction, and they are producing a photon, which is virtual photon, and then giving you quarks and anti-quark, in which a quark itself can be excited and give away gluon. Gluon do not exist in nature, so they will eventually form other jet. So secondary products will be generated. So this is first one kind of primary diagram, tree level diagram. Virtual particles have the property that they do not follow energy momentum conservation, but at all vertices, energy momentum conservation have to be followed. These kind of things have to be taken care. All the energy momentum conservation which we have been having in the classical mechanics, they have to be followed. All the properties of quantum mechanics have to be justified. All the observations predicted by quantum mechanics have to be predicted by quantum field theory also. So it's not that it's a different thing which will predict something different. We can go to next page. It should predict everything, but it should be predicting relativistic particle and should be free from all the troubles earlier theories have been having. So here I have written Lagrangian density, equation of Lagrangian density. It may not be familiar to everybody. It's for quantum electrodynamics. Psi you can assume to be electron, and this F mu nu you know are the field, electromagnetic field. And this IE mu sitting with the del mu operator gives you the interaction between fermions and the vector electromagnetic field, which is now will be called vector boson. You can write using action as in classical mechanics, minimizing the action. You can write Euler-Lagrange equation. So conventional Euler-Lagrangian equation in left-hand side of classical mechanics gets converted into quantum field theoretic Euler-Lagrange equation. And if you see this psi alpha x, I would like to explain this psi alpha x. Alpha is the spinor property of this wave function. Spinor property I didn't discuss, but when we solved the Schrodinger, this Dirac equation, we got 4 solutions. 2 solutions were for the particle electron, and remaining 2 solutions were for anti-particle. These 4 solutions in Lorentz space, means our Euclid, this space, space-time, which is called which forms actually SO13 Lorentz group. In that one actually gets 4-dimensional spinor representation. This is a little detailed group theory, but don't worry, just take psi to be 4 component. So alpha is that component index, x is the position, and this wave field is spread over all the space, and then integration is over momentum. Spin is summed over e to the power minus ikx is the wave property of this field. Cs is the creation and in creation operator, annihilation operator, and d dagger. The next one is the creation operator. They will create particle and annihilate antiparticle, and similarly the other one will create antiparticle and annihilate the particle with the psi dagger. And U and V written here are those spinor solutions which we talked about, these 4 solutions. And similarly, you can explain the vectorial electromagnetic field potential A mu, where mu is the Lorentz index here. So we can move to the next page. You write the Feynman rules from this theory, and these are the simple diagrams associated with the simple factors you come out with, and then you can explain any scattering process between the 2 particles, like in the vertical, this third diagram is 2 scattering processes of electron with the photon, and I can rotate that diagram, and then it can become two electron and positron annihilating, giving 2 photon. And so many processes may happen and can be calculated. Scattering section can be calculated, cross section can be calculated, verified with the observable observed experiments, and moving forward to the next page, we can see whether theory is predicting correctly or not. But it's not the only thing. There's earlier diagrams were only tree diagrams. This one I have shown is a 1 loop diagram in which this virtual photon itself again creates electron and positron, and that annihilates and again creates a photon, and then eventually gives you electron and positron. So electron positron annihilating into electron colliding and giving electron positron. These type of diagrams are not forbidden in the theory, and therefore they may appear, and they give divergences also. We need to remove these divergences, and not only 1 loop diagram, with any loop diagrams. So all other diagrams have to be corrected. It's a very complicated business, so people do not go beyond 2, 3, 4, 5. I mean, quantum electrodynamics case, you can go to higher order, but quantum chromodynamics and other complicated theories, you have to stop after 2 or 3 loop diagrams. But you have to check the consistency of the theory, whether it's renormalizable. There is a gauge parameter dependence in the quantum in a vector boson theory. Even you can see in electrodynamics also that there is gauge dependence, and that has to be consistently checked. And there are so many complications. It requires 2 to 3 quantum field theory courses to really get the grab on the renormalization. But it works, and it works for the current theory of particle physics. So next page, please. And this is done perturbatively, 1 by 1. You calculate 1 loop diagram, and then calculate 2 loop diagram, and then gradually improve on your theory. And that's the only possible analytical way of handling complicated problem. If you want to solve x plus sine x is equal to 1.2 or 1, x plus sine x is equal to 1, you cannot calculate it exactly analytically. You can only calculate perturbatively. You assume some value of x and then calculate and find new value of x and then calculate and keep on going unless you get the required precision. And that's the way of handling all complicated mathematics, which include the transcendental functions or complications like in renormalization theory. So so it's a kind of fate, but it's a boon also. We don't get troubled, and with a significantly large but some effort, we start getting the accurate results very quickly. Next page, please. So here I have listed these 4 fundamental interactions, and in earlier lectures also these interactions have been discussed about gravity, electromagnetic, weak and strong interaction. Gravity, we know all the massive particles feel. Electromagnetic, only those particles which are charged, electrically charged, they experience electromagnetic force. Weak interaction is actually felt by isospin particles, so it will not be felt by gamma photon or gluons, but only the isospin particles. All the matters particles are isospin. Those which are isospin non-zero will experience this, but those which are isospin singlet, they will not experience weak interaction, like right-handed electron, right-handed neutrinos, or whatever. We are still in the previous page. And those particles which are color particles, quarks, are particularly color particles, they feel a strong interaction. And a strong interaction is not the interaction between the protons and neutrons. A strong interaction is the interaction between quarks. Interaction between proton and neutron is actually nuclear interaction, and that is different from the strong. The cumulative effect of a strong interaction. And I have written the strength of these interactions in the next rows. And we know that we only have very small control on the gravity. We have set up the GPS system. But electromagnetic theory, electromagnetic interaction, we have almost all the control. That's why we have developed so many things controlled by electromagnetic interaction. Weak interaction, we don't have almost any control on it. It happens only in the weak decays. And in strong interaction, we have a control on a small scale, which we use to recreate the energy or destroy things, of course. Next page, please. So quantum theory. Yeah, so I want to mention one point here, that no quantum mechanics was developed for gravity, weak and strong interaction. Only quantum field theory were developed for weak and strong interaction. Gravity is still struggling. I mean, people are still struggling to quantize the gravity. So in this page, I have listed these particles of a standard model of today's unknown today. There is no other particle discovered yet which is as fundamental as these particles. So upper block is for quarks, lower block is for leptons, and the right hand side these Z, gamma, W, and G are gluons. These are interaction particles. They are also particles now. Particle wave that trouble you can carry lifelong, but I can call them particles here. Higgs is recently discovered around in 2012 at LSC. So this completes the picture of today's alphabet of the nature, that these are the particles, and weak, strong electromagnetic and gravitational interactions are the grammars. These interactions are our grammar. That how these particles will interact is the interaction. This electron will interact with the electromagnetic field by psi bar I gamma mu a mu psi. That is the type of interaction. So these are the alphabets, and then that is the language, this grammar. And going to the next page, when this standard model of particle physics was actually proposed, these many particles which are cancelled here were not discovered, but they were proposed in the theory. There were certain hints about existence of these particles, but precisely that number of particles and in that precise connection was not there, and they got later discovered, and that's why we believe that standard model of particle physics is the most consistent theory to precedential accuracy. Though there are questions on the standard models which it doesn't address, we hope that we will come up with a more consistent theory in future, which will incorporate gravity also in it. Moving to the next page. So from meter scale, introduction of the first instrument to measure any physical measurement, we have moved to Hughes detectors. The right hand top is the CMS detector. You can see track standing left corner, left bottom corner. This LSC ring, you can see 22 kilometer ring. And the bottom right is the actually Hyper K experiment, where you can see two people sitting on a boat. So this is the size of the experiments. In the left bottom corner is the ice cube experiment, which is way more bigger than the Eiffel Tower in the bottom right. And the near to the meter scale is the LIGO experiment, which detects gravitational waves produced by collision of heavy massive objects like two black holes or so. Next page, please. So we are optimistically looking for a theory more elegant than a standard model, which also would be replying the questions a standard model fails to address. And we are enthusiastically hunting for the quantum theory of gravity. We never know when a whole new world opens up for us to understand. And with this statement, I would like to stop. Thank you.
Thank you very much, Ram sir, for your wonderful talk. We have got number of questions, but
Yeah.
due to time constraint, we cannot take all the questions, but a few of them. And I would also like your permission to share your email for the students to contact directly to you.
Sure. You can share the email, and with the restricted, permission, you can share my WhatsApp number also. I can reply there also.
Okay, sir. So let us now take few of the questions.
Yeah.
One question is from Talo VB. He's asking, what is the difference between the non-relativistic and relativistic quantum mechanics?
So non-relativistic quantum mechanics assumes that my kinetic term is actually p square up by 2m. Like non-relativistic quantum mechanics is not worried about the velocity, the allowed velocity limit. It's not worried about it. So velocity is like we had in the Newton's equation, that velocity v is equal to u plus at can go to any large value. Similarly, in non-relativistic quantum mechanics, this momentum can go to infinity. But allowing that kind of things is not permissible. You calculate the expectation value of velocity, which is going beyond the velocity of light, which is not observed experimentally actually. So these kind of problems it has. So non-relativistic quantum mechanics had to be replaced by relativistic quantum mechanics to be a Lorentz covariant theory.
Okay, sir. Another question is, what is the physical interpretation and significance of isospin of a particle?
Okay, this is a slightly tricky question. Isospin of a particle is a quantity which is quite similar to the spin of the particle. Spin of the particle can be a similar thing, can be same for different kind of particles, and similarly isospin can be same or different for different kind of particles. So physical interpretation of isospin, I'm not sure how I can explain it, but
No problem, sir. You can explain it on the email for the detailed discussion.
Yeah.
Another and the last question which I'm taking. Sir, is it possible for gravitational field to split spectral line? Is it possible for
Gravitational field, yeah. So the interaction strength I wrote um, in one of the pages at the end. Strength of weak interaction compared to electromagnetic interaction is of the order of 10 power minus 42. So if you want to split it with that precision, though you will not be able to measure it, but you can split it. The electrons and protons are of course massive objects, so definitely gravity will work. But there are other things like Lamb shift is one of the things which is actually correction on the masses of electron and proton due to their movement, their due to quantization of the field. There's a higher order corrections as we discussed in the renormalization section. So that correction in the mass gets, though very weak Lamb shift, but non-zero correction due to change in mass. Gravitational correction will be so tiny to really observe in any near future. So, and also there is one more point is that we also do not know that at atomic scale how gravity works. So we are still hunting for it. We are trying to look for it. What is the kind of gravitational interaction at the atomic scale? Classical scale, we know it is gmm by r square. At the terrestrial astronomical scale, it's a relativistic theory of general theory of relativity. But at subatomic scale, we don't really know that how gravity is. But it's very weak.
Okay, thank you, sir. So this concludes the first lecture. Thank you very much, sir, for accepting our invitation. And for
Thank
more
you.
questions, I will give your email to the participants.
Sure.
Yeah.
And thank
with
you for
your-
holding on it. It was really terrible experience with the Zoom.
No problem, sir. It happens, sir. It's very normal these days, especially for we people over the internet. Anyways, so our next speaker, Dr. Pramod Gupta, is present here. I would like to request Dr. Yana Madam to kindly introduce our next speaker, Dr. Pramod Gupta ji. Over to you, ma'am.
Thank you so much, Dr. Ram Awasthi, for accepting our invitations. We are very thankful to you. And I hope our participants really enjoy your lecture. It is very informative and valuable for our participants. Thank you so much, sir, for giving us your precious time today. Thank you, sir. Now, let us welcome our next speaker, Dr. Pramod Kumar Gupta. He is my best friend. We work our PhD research together in the same lab, Special Center for Nanoscience, JNU New Delhi. We did our research work together, and now he is working as postdoctoral researcher in the Nanoscience Research Institute, Hanyang University, South Korea. We are so proud of you, Dr. Pramod Kumar Gupta. Thank you so much for accepting our invitations. So I would like to, for our participant, I would like to introduce our next speaker. Dr. Pramod Kumar Gupta received his bachelor and the master degree in physics and electronics from Biosensor Development under the collaboration with Jamia Millia University and JNU New Delhi. At present, he is working as a postdoctoral researcher at Nanosensor Research Institute, Hanyang University, South Korea. His current research interests involve on the designing nanomaterials for developing efficient nanoenzymes and biosensor for point-of-care devices. Dr. Gupta has published many reputed international journal publications in many reputed journals, and he is very skillful in the synthesis and characterization of 0D, 1D, 2D and 3D nanomaterials and their development of electrochemical biosensor for the range of analytical, including oxytocin, Vibrio cholera, vitamin D, and oral cancer biomarker. Sir, thank you so much for accepting our invitations. And now it is over to you.
Okay. Uh, is my audio is clear?
Yes, sir. Yes,
Okay.
sir.
Okay. So first of all, I am thankful to you for nice introduction and inviting me for this lecture. And I am congratulate you for organizing this successful webinar. Hello.
Sir.
Yeah. Okay. So without wasting time, I am going to start my today's talk.
Yes, sir.
And
There is your PPT, sir. Yes.
yeah. Okay. Is it visual?
Yes, sir. It is visible.
Oh, okay. Okay.
Yeah. Make it in full screen, sir.
Okay. Now it's
Yes,
better.
sir. It's fine now. Yes,
Okay.
sir. It's better.
Okay. So my talk title is physical sensors and their applications. Hello. Okay. So physical
Yeah, we
sensor
can hear
and
you.
applications. So here I am working as postdoctoral in Nanosensor Research Institute at Hanyang University. Actually, Hanyang University has two campuses. In one is Seoul and second one is Ansan City. So I am in Ansan City of this university. Okay, so today the overview of my talk includes about the introduction about the sensors, why we need sensor in our life, and how it is going to make flexible our life, and sensor classification, and how and why to choose a sensor, means a specific sensor. How can we choose one for a particular application, and a physical principle about the sensing and their application, and there are some characterizations, means characteristics. So to define the sensor quality, means how to check the sensor is good or bad, and in the last conclusion. So so when we are going to discuss about sensor, the human body inbuilt with some sensors, like you can see, like we have ear, eye, smell, uh, like a nose to smell. So these are the sensor, biological sensor inbuilt in our body. So what are they doing? Like here is listening voice, which it is visiting some places, or like you are getting the appearance of some substances through your eyes to your mind and making some decisions. So sensor is like that. You have to sense some environmental things and make these signals transfer to the system or human, and we have to make decision according to that. So what is sensor? So according to the American National Standard Institute, they define like a sensor is a device that provides usable output in response to a specific measurement. So it means like if we have one input signal, the sensor processes it in a output signal which is measurable by the system or human being. So sensor requires an input. Input means stimuli to process. It could be physical or electrical, any signal. And output, usually we see like in sensor, the output signal is electrical one, but it is not necessary for all cases. And in some cases, we have to add one more step to make it measurable signal. So there are pictorial description of few sensor that we are using directly or indirectly in our daily life, like color sensor, gas sensor, LDR, smoke sensor. Usually you can find it in buildings, temperature sensor. Most of the experiment you are doing in your lab using temperature sensor in form of thermocouple, and rain sensor also, like usually you see in the news channel how millimeter rain was there in last day or today, like that. So the rain sensor, they tells about the how was the rain quantity, like a water flow sensor, it, and IR receiver means infrared receiver, and ultrasonic sensor for distance measurement means, and there are many lots of sensor, hearing sensor, touch sensor, but we have to know how to use, means we are using these sensors, but we don't know the name of all sensor and what is the mechanism behind them. So today we will discuss some of the sensors which is like based on the physical phenomena, because classification is quite difficult. I will extend it in our next slides. So let's. So first of things comes in our mind, how we need, why we need the sensor, what is the advantage, disadvantage, like that, and why we use sensors. So first of the things, you can, I have given some bullet points, means if we have to sense our surrounding, we are in, we can in any environment. The environment could be toxic, could be hot, could be any you can say any kind of temperature, pressure, gases could be in environment. And if we are going in that environment, it will affect our body. And sometimes it could be dangerous. Like some before some days, you see there are some gas leakage were there. If human is going to sense that one, he will not come back. So to sense the surrounding, determine the physical state, means how, means like same thing, what is the physical state of the environment, and interaction of with environment, and yeah, it also help in protection human, health protection and self preservation most of the time. And many automatic equipment are based on the sensor. If there is no sensor, the automation of any system could not be possible. So sensor are very essential for the nowadays. So there are some benefits of sensor also, it accelerate process and make them more accurate. Means any process you are doing, it can make it easier and with more accuracy. And it can collect the data, means real time data, and it can process the data with accurately, readability, and continuously. And it also increase the productivity and reduce the cost. Anywhere you are using sensor, it definitely it will decrease the cost, is manpower will be decreased, and it save energy also, like in case of electricity, in case of any machinery you are using sensor, then without any requirement it is not going to work. Means it will be operated with the sensor. If something is there, means there will be some condition. If it is happening, then your system will work. Otherwise, it will be stopped, like that. So this is the size about the classification of sensor. So in my point of view, classification of sensor is quite confusing, or you can say difficult, because there are many criteria, means on the based of power source, output signal, there are many criteria on which you can classify your sensor types. So I have given some major here, major three, depending on the power source, depending power source, it could be active or passive. So I have given these bullets and I will explain it in next slides. Like output signal, like the output signal could be in log or digital form. And conversion step means how many steps are there to convert your input signal to readable output. So there are some other sensor other classification based on the measured value, means what kind of quantity you are going to measure. Like physical principle, what is the principle behind that sensors, and what kind of materials you are using, like organic, inorganic, or in case of size, nano, some people, like I seen, if we are saying nano sensor, they will define that sensor having nano size, but it is not correct. If we are using nano materials, then it could be called a nano sensor. So, and like measurement, like thermal, optical, means depending on the application, it could be classified depending on the application also. So let's start with all these bases. So first is the active and passive sensor. So active sensor means it don't require any external supply, means it work independently, means it take the input, it get the biasing from the input, like photovoltaic cell, like it is going to take the power from sun and converting it in electrical signal, but it don't require any biasing or input. It is directly taking and delivering something. Like thermocouple also, like it taking heat and converting into electrical signal. So like piezoelectric also, you are going to make some pressure on piezoelectric substance and it is going to produce some electron and holes, means in the form of voltage or current. So its own physical property of sensor vary with respect to applied external effect in case of active sensor. So therefore it is also called a self-generating sensor. So any sensor which requires to input energy to the environment in order to retrieve the measurement is active. So in alter to this, passive sensor requires some external supply or external energy. They need extra stimuli or voltage, and sensor are able to retrieve a measurement without actively interacting with the environment, because they are we are going to give the external supply, so they are have not to take much biasing or input from the source, means your input. So like strain gauge, nitrometer, barometer, these are the some sensor, we are going to bias them, giving some supply, and after applying some input, it is going to convert in output signal. So second is analog and digital sensor. Analog digital means it depending on the output signal. Some sensor are producing signal, output signal in form of analog, and some in digital. So the difference between these two. So comparing analog and digital is more, have more accuracy, and it can interpret, yeah, in case of digital, digital in 0 to 1, but in case of hmm, hmm, but the circuitry of digital is quite complex, means accuracy is there, but circuitry or system will be complex. And this with high accuracy digital sensor are used for pressure monitoring in tires, like monitoring airflow, and very much in medical devices. And next to this, there are direct and indirect sensors. So direct sensor means it can convert the electrical signals into electrical, non-electrical to electrical. And the indirect means it like they requires one more step to transfer the measured signal into electrical. So these are classified depending on the steps. This is one step and this is multi-step or two-step process. And depending on the measurement, or means what kind of quantity we are going to sense, this could be as a large range. You can see that can be mechanical, optical, electrical, acoustic, thermal. There are many kind of like a force strain, like you can see it. I am not going to in detail because it's quite complex. So, and depending on the phenomena, means the principle of detection, it could be like classified in acoustic sensors, biosensors, electrical sensor, magnetic sensors, optical sensor, thermal sensor, mechanical sensor, and these are the quantities, means input quantities, and we have to convert it into measurable one. So, and depending on the property, means sensor property, it could physical property. If we are using physical property, physical, chemical, biosensors, like that. So that's why I tell it is quite complex to classify these sensors. So in many books, many papers, many data sets are there, but they are conflict with each other. So one of the there are I summarize all the sensors here based on the power source. Like it could be like classified in many types. So okay, so how to choose a sensor? So sensor choosing is very important. It depends on the what kind of property we are going to analyze, and how the signal will be readable. So environment factors, it depends on the environment factor. Like environment have the some could be some temperature effect, humidity, corrosion, overrange protection. Like many factors are there which can affect the performance of sensor. So first we have to observe what kind of conditions will be there during the application of the sensor, and you have to make your sensor free from these kind of effects. So, and second thing is the economic factor. If you are going to fabricate any sensor or design any sensor, like you you should have to minimize the cost, and whatever material or any system you are using, it should be available everywhere. And what is the lifetime? Lifetime is how long it will work. And these are the sensor characteristics, means it defined by the sense in terminology like sensitivity, range, stability, linearity, response time, frequency response. It depends on the technique. And okay, so so next to this, I am going to focus on these parameters like a sensor characteristics in the next slides. So I want to first introduce about the sensor. What should be the precautions to design a sensor during the application, and how to sense the how good the sensor is. So there are some characteristics of a good sensor. Good sensor, like a sensitivity. First terminology is sensitivity. Sensitivity means With low value of input, there will be high value of output. It means the ratio of change of output to the change of input should be high. Means a smaller signal could be readable from the sensor. And here, a second thing is precision, means how precise the output signal for the same input. Means if we are going to run the system like a one sensor multi-time, or we are desiring multi devices, means a number of devices, this should be like follow the same output trend. Like here in the second graph, like this is the first one, ideal response there. If it is precise, it will follow the ideal response. And if it is imprecise, then there will be much noise. That noise could be like observed due to many factors. So like I will tell you in the next slides. And third one is resolution. Resolution is the ability to detect a small change in measured parameter. Like means how accurate, like resolution means if we are going to sense any signal and outcome is like a 10 volt or 10 milliampere, then the resolution will be like how means plus minus how much value will be there. It could be minimum as like as soon as could be possible, and generally for commercialized like a 0.5% or sometimes like a 5% also mentioned like that, but that will not work well. So depending on the application, means some application required much accurate things. So and noise should be lower, means noise could be from the some interference in the environment, and that can affect your output. And hysteresis means like the sensor will tend to read the low with an increased signal and high with decreased signal. And this is the hysteresis is the common problem with any pressure, like you can say the ongoing and incoming path are different. Means during the observation, I mean going up one side, they are like containing some effect in their system. And characteristic of sensor is one is the linearity, how linear the output signal. Means linear means the input and output will have a strong relation, means output should be directly dependent on the input signal. In that case you will get a linear response. If it is not linear, then you will get response like this one, like the fourth one in graph, or it could be any type, but it will not linear. It could be like here, it can be saturate after some time, like that. And of the one element, one parameter is offset error. Offset error means comes from the like uh, biasing of the system, biasing, or if it is it has some like you can say predefined value stored in the system or sensor memory or like that, it will give a over like a over response. Means the linear curve will be something higher at each point. So we have to like accurate these things by calibrating the sensor if we are getting like that. Means and in case of practical sensor, this could be like the property of the sensor depend on the material characteristics, shape, size, and there are in like many parameters that can affect the sensor. So if it is something is going to disbalance, then such kind of problem you can get. The curve like offset is here, like offset could be in positive and negative also. So, and next is the response time. Response time means how quick you are getting the response after applying the input signal. And yeah, like today's, if we are talking about the today's scenario, like in case of coronavirus, yeah, everyone is, uh, it is difficulty for everyone. But nowadays, like if you are going for testing, they are getting report within 30 minutes. Yes, they have optimized the like response time, and many sensors are there which means by which you can get the report by 5 minutes also. So that is called the response time. How quick the sensor means, a sensor could be any type of sensor. So it will take little bit or more time. It could be the property of the sensor. So, but for good sensor, response time should be minimum. And interference means the performance of the sensor should be free from the interference, means the environment in which we are going to work, like in a closed box or it could be like a physical property like magnetic field. There are many signals, microwave signals in your environment, temperature, pressure, or some fluid are could be there, or other substances are could be there like that. So they can affect the sensor properties. So we have to make sure that our sensor is should be free from the environment effects or interference. So next is the repeatability. Repeatability means how long means your sensor giving the same response with the cycles. Like in case of any sensor, like the temperature sensor is there or humidity sensor there. So once you use one, two time, three time, like you have used, and after some time you are saying like observation is not accurate after some time. So that will be not a good thing. Means it should be same for as long for many cycles, means long cycles like that. The same output should be repeatable. And reproducibility means if we are making a sensor and fabricating it again and again, it should be accurate and give the same response. Means repeatability means it should repeat the same performance as for the first time. And last one is the storage time. Storage time means if we are going to hold your sensor, it could be any type of sensor. There is some one is the working life and one is the stored life also. Like if you are not going to use any sensor and you are going to keep them in a such environment, in could be like a uh, that could be physically infected, means affected or not, but there will be is some storage time, and this storage time should be high so that you can preserve it for a long time in working and non-working condition also. So uh, okay, so this is the main or important things to discuss, like a physical principle of sensing. So I have chosen some parameters like capacitance, inductance, resistance, piezoelectrics, Seebeck, Plenty, and light. These are the parameters by which we will observe like how can we define a sensor, how can we fabricate sensor by on the principle of these parameters. So first of all, I am going for capacitance. Actually, I have simplified this talk according to the bachelor and master students. So the capacitance, all know about the capacitance, means it's the combination of two parallel plates having opposite charges, and due to these opposite charges there will be a potential difference. And capacitance, and capacitance is uh, the ratio of charge upon voltage, and its silent zero means the permittivity of the dielectric constant, means the permittivity of the dielectric. So this is a simple rule for capacitance. And next slide we will see how the capacitance depend on the other parameter. Like capacitance is directly proportional to the area of the plates, but inversely proportional to the distance between the plates. So it is defined here if we are going to change the area, means overlapping area of the plates, means or the distance between these two plates, then there will be a change in capacitance. So depending on these situations, how can we design the sensor? Like this is the very simplest one. This is the coaxial capacitor, cylindrical capacitor, and their coaxial inner side is negative charge and outer side is positive charge, like that. And here, this is the core, coaxial here, and this is the core. You can say dielectric. Okay, so if there are two parallel plate capacitor and we are inserting here a dielectric, then what will happen with the length of the displacement, with the displacement of this system, means substance, the capacitance will be changed, means it will sense the displacement, means if it is going to move forward or backward, the capacitance will change. So depending on the capacitance, there are many sensors, whatever means that are using in nowadays in our daily life. They are touch screen. You we all know and using touch screen in our mobile, in some iPads, laptops, like that. So how it work? It is like a capacitive touch screen are there. There's it's two layers, and between these two layers there are many capacitance, and these capacitance are attached with some coordinate, means some locations on the board, electric board. So whenever we are going to touch, you can see there is a particular location here, the location will be here, like dot same. So if we are going to touch it, the capacitance will change, and it will give the input to the system, and your electronic system will sense this and do the whatever you want to take from that system. Like here, this is an example of capacitive sensor for measuring the water level. Like this is the h distance, the total h is there, and like if there is some extent of water in this pot, then there will be it will work as a dielectric here, and the between parallel plates there will be some capacitance, and if it is going down to h0, there will be a signal, means no capacitance, means it will buzzer the alarm, like in our coolers. Coolers or we usually use in our home. So if there is no water or low level of water, the buzzer start the alarm, like it would and you sense that water level is low. So this is a capacitive load cell. Load cell usually we use to measure the load, means if anything, like if you are going to press load cell, actually the load cell is used for like a high weight, not for the simpler one, like in case of trolleys and many things, means vehicles are going to loading for loading and unloading, so they are using load cell usually. Like if we are going to give the pressure here, the capacitance will change, and this capacitance is calibrated with the voltmeter, so that you will get the what is the weight on the load cell. So this is simplest applications of like capacitive sensor, and you can make or design many sensor, many more sensor depending on this property. And here, like this is the capacitive biosensor, like these physical properties are going to use in like biokind of detection. Like here we have applied a frequency, and this is the capacitor, and capacitor plates are there connected with this circuit, and this is functionalized with antibody. So antibody, and after that their target elements like could be antigen, and if they are going to immobilize on the surface, there will be a charge difference, because like our body has also some system like this is called the bioelectronics, because our body is able to flow the current. So there are some change in the capacitance, and if this capacitance increase or decrease, there will be a lag or lead between the voltage and current. You can directly like measure the capacitance also if we are going to like biosensor. But here this is other one, like a by the varying the capacitance, you can also sense the phase difference, means the lag or lead between the voltage and current. And next to this, induction. Induction, like capacitance, inductance. Okay, inductance is we will know about very well, like we all have read about inductance, so I am not going to in much detail about that. But like we should see the how the like EMF appears, and how it depends on the number of turns in coil, like a flux change, and other properties. And second one is the mutual inductance. So here, like if one coil is nearby the other, so due to change in flux, there will be induced current. So these are the two basic properties of inductance. So let's see how can we design some sensor on the behalf of these like principles. Like like here you we all know about the metal sensor. Whenever we are going in shopping malls or any going through in some security system, there will be a instrument called metal sensor, which is going to detect if we have some unwanted things or metallic things, especially metallic things. So this is the normal structure, like it has some oscillator, and it will oscillate and generate changing magnetic fields. And here is the current sensor inbuilt with this device. It is going to contact with some metallic region, and it will change the magnetic field, and there so that there will be a change in current, and it will buzzer that it has something, some metallic things. If it is not, then there no metal. And after that, here is the inductive sensor, like for displacement displacement sensor using inductance, mutual inductance. Like here, this is the input coil, and these are the secondary coils, but their turns are just opposite. Means if we are placing this, it's like a armature in middle of that, that coils, then there will be cancellation of like current induced in this and this coils. But if we are going to displace this coil from anywhere, means any side, upward or downward from the middle position, it will sense some current depending on the, like a upward or downward more like a displacement. So this is a simple application, like you are going to use inductive property to sense the metallic kind of things or displacement of any object. Okay, so next is the resistance. We all know the resistance is the property of material that resists the flow of current. So this resistance is depend on the length, area, and resistivity of the material. And resistivity is the specific for each material. Some material have high resistivity, someone has low resistivity. So depending on our application and required accuracy, we use different kind of materials, or sometimes we make alloy, and many various paths are there to improve the property of resistance or resistivity. So like how we can use this resistance for temperature sensing. Like the specific resistivity or conductivity of the materials change with temperature. You can see with the equation, like if temperature is going to change, the resistivity of the material, the specific resistivity or conductivity, it is going to change. Like here, this is a plot of tungsten. So it is going to work in high range of temperature. So there are many materials. I will show a table in the next slide. Means depending on the temperature and resistivity. So okay, so there are like some resistive temperature detector we can fabricate using platinum. Like here, this is the example of platinum. Means it can work about from 200 to 600 temperature, and this is the like normal things. Okay, I am going to left side. It is not so important actually. Okay, so here we are going to apply the change in the resistance by strain. Means how the change in the resistance could be could change the sense the strain. Like if we have a wire having area or cross section area of A and length L, and we are going to make a force, apply a force to stretch it, then there will be a change in resistivity that can be defined by F by A. So in this way, like there are some condition also, like if the cylindrical conductor is stretched by applied force, the material volume like stays constant, means the volume will be same, but length will increase. So in this case, resistance will be rho by V into L square. And yeah, and this way, like you can say, like if we are going to make some forces or apply some force on the wire, it will get strained, and this strain could be like a sense in like in form of resistance. And here is the resistance for my like moisture or humidity sensing, like you know, like material, yeah, like every material have different specific resistivity, as I told in previous slide. So moisture like a dependent resistor can be fabricated by of the hygroscopic hygroscopic material, which is like a specific resistivity is strongly influenced by the concentration of observed water molecules. Means some material have property to absorb the moisture from the environment, and due to absorb like moisture, its resistance is going to change. Some like hygroscopic material like copper sulfate, phosphorus pentoxide, like silica gel. So they have ability to absorb the moisture, and due to that absorbance of moisture, its resistivity is going to change. So this is the prototype of a sensor, like this is the interdigital electrode. You can say they are not going. There are two terminals are there. They are not going to touch each other, but there is a layer of these polymer matrix, like a like here I have given the description, like it comprises of ceramic substrate and printed like electrode to silk. And electrode are metal conductor, means its conductivity should be high, and we are going to overlap this electrode with help of some polymers, means, and you can also induce some like conducting material also, depending on your application of, or you, if you want high sensitivity, or depending on the condition. So if it is going to absorb some moisture, the layer like in between these two electrodes, there will be a layer of polymer, and this resistance will be changed with the concentration of absorbed moisture. You can say like here you can see in graph, like this the resistance and this is the moisture. So depending on the condition, like it could be you can fabricate it like a depending on the material properties, what kind of polymer and what kind of matrix is going to overlap on the system. So in the like moisture sensor, gas sensor also can be fabricated, like if our surface have ability to like absorb some specific kind of gases like CO2, like carbon monoxide, or some dangerous or toxic gases could be there. So nitrogen, like anyone. So we can make some resistive platform for oxygen sensor depending on the material property. So we have like usually like as I memorized, like before some days back, like in case of coal factory, like coal tunnel or some like plants, people use some like a pets, like a pigeon or parrot, and like that. They like if they sense like there is something going wrong, like could be gas leakage, they throw them in that area. If they are coming back, then okay, it's okay. But if they are not coming, that they like confirm that this there is something not going well, means could be toxic effect, like gases could be there. But nowadays we have not to do, work smarter and use like a gas sensor, like a humidity sensor. There are many sensors are there. You have to just put your sensor, and if something is going on, the real time detection will be there, and it will inform you by a measurable signal. So next to this, I am going to discuss about the piezoelectric effect. The piezo, the word piezo comes from the Greek. It means like press, as its principle, like a working principle, like press means piezoelectric effect is generation of electric charge by the crystalline material subjected to stress. The effect exists in natural crystals such as quartz and yeah, some human-made ceramics and some polymers also. So in these substances, if we are going to make pressure in transfer direction, it will like appear will be a potential means potential. Okay, so I have written here, like if the crystal is stretched along x-axis, the charge opposite polarity is built along the y-axis. Like this is the x-axis, you're going to make force, and then charge will be appear transfers to the force direction. So let us see in less light how can we use this. Like yeah, we can use this principle to detect the pressure or force in terms of potential difference, or we can sense the frequency. If frequency is there, there will be some frequency means it is going to like a mechanical frequency, it is going to suppress, and like at a particular interval, it will make the current flex, change in current. And yeah, piezoelectric effect you can sense in your, especially in your mobile, because we all using mobile, and there is a vibration is due to like if we are going, yeah, this alter properties, if you are going to apply some potential, it make vibration also. So best example of this sensor is the vibration in your mobile phone. Okay, so next is the pyroelectric effect. Pyroelectric effect is it is quite similar to piezoelectric effect, but there's some minor difference. Like you can say, like piezoelectric, the pyroelectric material are used in form of thin slice as we use in piezoelectric, and and electrode deposited like a you can say, okay, an electrode deposited on the opposite side to collect the thermal induced charges. Means if we are going to change the thermal flux, there will be like two electrodes, they will induce with the some charges, like here. By the thermal flux, there will be appearance of voltage difference between two. This is the ideal first initial condition, and after change in flux, thermal flux. So this is the good sensor for to sense the heat. Like a pyroelectric sensor is essentially a capacitor, you can say, and which can be electrically charged by the flux of heat, and sensor does not require any electrical biasing, and it is a direct converter of heat into electricity. It and more of this, it needs only the appropriate electronic interface circuit to measure the charge. So it is very good thing to change the like heat into some amount of potential difference. Okay, so here we have given example of pyroelectric effect for heat sensing. Like there's a sensor, we are providing some heat, so it will generate some charges, means in case of potential difference, and then can be gone through to the load. You can say this is resistance. Resistance means the load. It can work like that. And this is the some yeah, this and this one, like heat can be sensed in terms of charge and potential also, because with the charge and charge potential are interrelated to each other. And these are some equation to define how the heat source is going to change, means a temperature difference is going to make the difference in, like in this stored potential or charge. So next is the Hall effect. Hall effect is very useful principle for in material science. And Hall effect, like okay, it like Hall effect is the, he discovered, like Edwin Hall, yeah, the scientist name was Edwin Hall. So he discovered, like when a conductor or semiconductor with current flowing, current flowing in one direction was introduced, particularly to a magnetic field, a voltage could be measured at right angle of the current path. Like here, if we are going to put in magnetic field, this current carrying conductor and flowing current in this direction, there will be some potential difference. So in term of sensor, Hall is either the like it could be used for voltage difference across the conductor, and or yeah, it could be used for like a Hall sensor, uh, could be used to detect magnetic field, position, and displacement of object. So, but in case of like if we are going to calibrate the displacement or position, or in by voltage, the current should be constant. Or if you are going to calibrate it in current, then voltage should be constant in the system. So this is the example for Hall effect current sensing. It is the fact that Hall effect depend on the magnetic field, means it can be used as a constant, like contactless technology. Means contactless means you are not going to make a shunt, like cut this wire to sense the how the amount of the current flowing those to this wire. You have to just place it around the wire, and Hall effect will tell you what is the amount of current flowing through this wire. So this is very useful for current sensing. And okay, so next to this, Hall sensor is also for position sensing. Like if some magnetic material is there having north and south pole, if displacement is there in some direction, it could be sensed by the Hall sensor. Like same principle can be used to detect the presence or absence of proximity of a magnetic field. So if Hall voltage could be changed. Okay, in the simple application, it may be like readily, you can say, yeah, the better application of this kind of sensor is our laptop. Yeah, in our laptop we use this one, like when you open your laptop or closing down, it will sense the displacement, and it turn off your system. So there's a Hall effect, for polarity sensing. Means polarity sensing means what kind of polarity, or in other way you can say what kind of material, like it could be N type or P type material, a semiconductor material, that could be checked by the Hall effect, depending on the polarity of charges, like depending on the pole of magnet. If it is N type, then negative charges will be there upside. If we like P side, there will be holes like a positive charges. So next to this is the thermoelectric effect. So thermoelectric effect is work on the two basic principles. One is the Seebeck effect and one is the Planter effect. So first one is the Seebeck effect. So Seebeck effect is the phenomena wherein a temperature gradient occurring between the two junctions formed by two dissimilar electric conductors or semiconductor cause a potential difference to be developed between them. So this potential difference allows electric current, you can see here like that. So it will develop a current between them, and this is called the Seebeck effect. Like here, two wires, like two different kind of wire, like one is a copper, one is the bismuth. We are going to attach that, and uh, and one junction is going to like warm and one is the cold. Like there should be some like temperature difference between the two joints, then there will be a production of current. So like, but the like wires or material should be dissimilar. For similar wires, there will be no like generation of current. And if temperature difference is not there, then also there will be no current. So, okay, the Seebeck effect is used for heat flux sensor. It could be used as heat flux sensor. Like heat flux sensor are based on the Seebeck effect. Like when heat passes through the sensor generate voltage signal. Like I told here and there, like if one terminal is like heated and one is cold, I mean the temperature difference, then and material are dissimilar, then there will be a production of like generation of current. So if heat flux is going through one junction, then it will produce some voltage, and we can calibrate the heat flux with voltage difference. And other application like Seebeck effect is the thermocouple. Thermocouple we usually use in our lab in any instrument having like a showing the internal temperature in the system. They usually use thermocouple. Thermocouple like this area, probe area is here like two dissimilar wires, and this like area is exposed to the heat, and due to that it is going to make some difference in current, generate some current. So we can optimize the heat with the relevant current. So this is the very usual thing that we are using in our lab. And next to this, yeah, here there are number of type of thermocouple according to their useful application range and name of material. Like composition of material, it is going to change the like thermocouple accuracy and temperature, and it means their characteristics could be changed by the composition of material. So day by day research is going on to improve the all the like applications, means improve the performance of sensors. So this is the list. After some time, there were many materials and many kind of paths may be there. So after that, next is the Peltier effect. Peltier effect is opposed of the just inverted to the Seebeck effect. Like in Seebeck effect, we put applied potential like a temperature difference with dissimilar wires and get the current. But here, if we are going to give apply some potential to the dissimilar wires, means like N type, P type, then it will generate current. One end one end will be the heat absorber, and the second one will be the heat releaser. So this is the basic fundamental about that, and this kind of Peltier effect, like a Peltier element, are going to use in many applications. Some of them cooling the systems, means in case of laser diode, means they generate much heat because and in cameras, where the CMOS transistor are there, means they are they produce much heat and generate the voice noise in the camera. Like many devices are going to be make stable with in reference of temperature, or going to cool the devices using that Peltier element. And yeah, okay. So next to this is the mechanical element. Like a mechanical element, you all know, like a IPR. This is a traditional one. Like a spring is there. We are going Newton's, yeah, force. If we are applying something, there will be some oppose of that one. So this is the basic fundamental. I'm not going in detail in this one. So yeah, after that, this is the sensor using cantilever. Like cantilever are commonly fabricated by silicon or silicon nitride or some polymers. So cantilever are very useful to designing some sensor. This is the diagram. This is the reference, and this is the practical. If we are going to attach something, means putting some load on the this terminal, this terminal, it will going to deflect, means deflection will be there. And if we are going to make apply a light source and detector, then we can sense this displacement easily by the at the detector, photo detector. So you can say the a force or weight could be sensed by this cantilever. So here I have designing this is design for any substance. It is substance biomolecules, like it could be used in biosensor also, biomolecules or other things, other substance is going to attach on this surface. Then there will be deflection, and deflection will be detected by using the angle of this deflection by using laser and detector. And some of the cantilever are also used nowadays. This is the kind of cantilever for uh, measuring the deflection. But people are using nowadays, they are going to attach a layer, extra layer on the cantilever, means by the chemical one. If we are going to skewage or bend the this surface, the chemical composition, or you can say the crack could be appear there, and that can change the resistivity or conductivity of that cantilever. So there are many ways to define or calibrate your sensor. not a like a ideal one, means for all the things. You can design, you can modify according your way. So yeah, and one more thing, like in the last, I am going to end my slides actually. So distance via light. Light, like light is the good way to make like measure a distance where you are not going to like physically measure the distance. So we know like distance between Earth and Moon around 385,000 kilometers. But you know how to like we can use the laser source to measure the distance between Earth and Moon also. Like and this distance will depend on the light velocity of light, means because the source is light, and time between like a signal between these two, means the time of this like transmit and receive of the signal. So you can say there like a laser ranging retro reflector, like a Apollo 11 also use that one to like measure the distance between one planet to other, like that. So here I am summarizing, like making my conclusion, like here. I believe like a small change can introduce big innovation. Like whatever we are doing, we have many systems, many principles, many data are there. We have to just change the some parameter or like give some creativity to change, means change or make the big innovations. And sensor is the like a device that receives, stimulates, and respond to this measurement signal. So this is normal things, means, and nowadays material they are used to design and fabricate a many different type of sensor, like like many properties are there. One property could be used for detection of many kind of properties. Okay, so with this conclusion, I am going to end my talk, and thanks to
Thank you so much, Dr. Pramod Kumar Gupta. It was a wonderful, excellent, and informative talks by you to our participants. And we have a lot of questions for you from
yeah,
our participants.
I know.
Of course, it will be very exciting talks for all the participants and of course for us also. So, sir, I will proceed you the questions.
Okay.
The first question is from Jenica Derry from Jain College, Pasigat. He asked, it is possible to make a sensor device for coma patient and for paralysis patient to make them responses?
Actually, yeah, means there are many devices. Like here, I am working in Hanyang University. There are some robotics department also. Means sensor they are using for paralyzed patient. Like if they are making wheelchair also, and some like a sensor which can read the mind or some sense like that, and they are working well also. I usually see on Saturday and Sunday they are practicing with these sensors. So it is possible, no doubt, with like artificial like like intelligence, like robotics and all the kind of things.
Thank you so much, sir, for your answer. The next question is from Assis. He asked how to choose a material or a nanomaterial in case of an electrical sensor.
Okay, electrical sensor, like it depends, means what kind of parameter you are using to detect. First one, like nanomaterial is basically nanomaterial, like in case of nano, the conductivity of material is going to drastically change. Usually it is going to high in case of nanomaterial. So they are like in electrical sensor, what kind of technique he like it is going to use. First one, like it could be electrochemical, or it could be only resistive using like a LCR meter like that. So if you are using LCR meter like that things, then you should take the conductivity, means the conducting material. And if you are going to change the surface of that material, is the resistivity will change, and that resistivity could be measurable using LCR meter or frequency response analysis like that. So for conducting, it depends on the technique. That's all.
Thank you very much, sir. The next question is, he asked, is it possible to fabricate sensor to detect the viruses using moisture absorbing material or polymer?
Okay, means a virus from the environment.
Yes, sir. Absorbing
Okay,
materials or
actually,
polymer.
actually, you can do night like that, because but like in moisture, like there are many substances are there, many carbonic elements, like alcoholic, like many substances are there, like including virus, bacteria, and all the things. But you have to first design a material having high specificity for a particular enzyme, bacteria, or anything. Means you have to first design your material, optimize your material. It should be sensitive for a particular kind of light or substance, so that after that you can make like that.
Sir, we have another question from Gitika Kumar Chakrabarti. He asked, does Vision, Google, or camera also use sensor? If yes, what kind of sensor are they?
EPS.
Night vision, Google, or camera
uh,
also have sensor? If yes, that what kind of sensors are they?
there are lots of sensor in night vision camera, especially like I told you, like a planetary element, using to cool down the CMOS sensor, like especially the CMOS sensor are there, the most powerful sensor for night vision cameras. So there are lots of sensor like to detect the environment, and the autofocus, like many sensor. In case of camera, you can't say, means you have not to ask their sensor. There are definitely many sensors, especially in night vision camera.
Thank you, sir. Sir, we have a lot of questions, but we are running out of time. So I have many requests from participants. If you can provide your email ID or
Yeah.
PPT for
Okay.
them.
Okay. Yeah. I will. Uh,
And sir, you have to wait for us. We have a validatory program after this. So for
okay.
10, 15 minutes, we need you. I
Okay.
request all the speakers,
Mhm.
all the eminent speakers and participants to join us for our validatory program. So it
Okay.
will just take few minutes. And after
Okay.
that, we will conclude our program.
Okay.
So I would like to request our coordinator of the webinar, Mr. Inukli Wang, to initiate the validatory program.
Thank you, Pramod sir.
Yes. Thank you.
Thanks a lot, sir. It was a nice session, sir. My dear participants, please wait for 5 minutes, just for 5 minutes, so that we can start our validatory program. Remember, there is an interaction between, there will be interactive session between the speakers and participants. So participants who want to interact, they can raise their hand, so that we can connect you via audio or via video. So stay connected. So give us 5 minutes first. Thank you.
So all the participants, sir, coordinator sir has told us that we will connect the participant to the speakers and to the coordinators. If anyone wanted to give the feedback regarding this program, please raise your hand here in chat box. You can uh, type the questions. We can connect you. We can unmuted you from video and audio. Just give us a few more minutes. Welcome back. Now we will start our valedictory program. I would like to request our head of the Department of Physics, Dr. S. Dainty, to inaugurate the valedictory functions. Madam, over to you.
Thank you, Dr. Yana, and I thank the coordinator for giving this time to uh, do the validatory function. I just wanted to thank, first of all the speakers, eminent speakers from different part of this nation. They have all have given their time, their valuable time in speaking forth from different topics of their renowned areas, and they have shared their valuable thoughts, their words of wisdom to enlighten and also to make the participants understand the subject in a very nice way. It's their efforts without which this program wouldn't have been successful. So my heartfelt thanks goes to all the speakers on behalf of the Department of Physics, and from my side and from the principal side and from the vice principal and from the coordinator side. We wanted to really thank each and every one of the speakers who have accepted our invitations and who have really done a big job in sharing your valuable thoughts with the participants today. And I also wanted to thank our principal, Dr. Minoray Modi, and also I want to thank our principal, vice principal, Dr. S.T. Chowdhury, and also I wanted to thank IQSC coordinator, Dr. D.P. Panda, for all the support and the encouragement and the funds that they have given in organizing this program in a successful way. Without the help of the college Without their constant support, this program wouldn't have been a big success. So I really wanted to thank all of them. Mr. Pajam Mgam and Sibo, Mr. Sibo and Mr. Manish Kumar Shukla for all their constant support, because they have been planning, working, we all have been working, and they were working day and night for this program for the last 20 days, more than 20 days, fix up the speakers and to organize this program in a proper way. So really I want to thank all of them for their success. I hope in the days to come, our department, our team will continue to have the same spirit of organizing many more programs. I wish them a great success in the coming days also. And I also want to thank the participants. All the participants have been patiently cooperating with us and all that, and they have been coming on time. There may be some delays from our sides. We apologize for that because of the network program, because we are doing this program from a remote area of Arunachal Pradesh, and this has been the first program webinar from our department side, from our college side also. So there may be some lapses, and I really apologize for the difficulties that you may have encountered. So kindly bear with us, and I hope that in the days to come, we will try to manage well. If there is any lapses, please feel free to send us in the feedback so that in the days to come, we will be able to correct it also. So I thank all the participants once again for bearing with us, and without your cooperation, this program wouldn't have been successful. From different parts of this nation, like Delhi, Haryana, even Tamil Nadu, and from Andhra and from Karnataka, we have participants around 375, and it has been a real great success for us in organizing everyone together in this webinar program. Thank you so much. Once again, I want to thank all the speakers and the participants for your good cooperation with us in organizing this program. So I will hand over the time to Dr. Yana for further interaction of the participants with the speakers. Thank you so much once again.
Thank you so much, madam. Now, I would like to request our coordinator, Mr. Inuk Livang, sir, to initiate the interaction with participant and speaker. Over to you, sir.
Thank you, Yana madam. So let's start the interaction with our speakers first. So we have Dr. Anup Nath and Dr. Pramod Gupta. So I first request Dr. Anup Kumar Nath to share his experience about overall webinars. Please, sir.
Hello.
Yes, sir. You are audible, sir.
Yeah, first of all, thank you very much to the principal of Jain College, HOD of Jain Physics Department of Jain College, all the faculty members, and especially my friend Anuk, and all the participants. And this is a very nice webinar, and I enjoyed talking here, and I would like to join in future webinar also, and I would like to meet Anuk also in your college. So we'll have some nice moments after this lockdown. Maybe sometime I will go to Jain College. I can interact with students also there. Okay, so this is a very nice webinar, and I hope the participants enjoyed my talk and learned something about nanotechnology from there. And for any query regarding that, and for any help, you have my email also, so you can mail also. I already got some emails and I answered few, and in the coming days I will answer all the queries. Thank you very much.
Thank you, Anup sir. Thank you. Thanks a lot. Your speech were very the talk on lecture on nanotechnology was very good, sir. Thank you so much once again, sir.
Yeah,
So
welcome.
I want to pass the mic to our Dr. Pramod Gupta, sir. He's away from South Korea. He's joining to us. So, sir, please. share your experience, sir.
Oh, I've seen that you people working hard to organize this conference and what I call webinar, and you make it successful. Like listen lectures like Dr. Anup and previous lectures also from Dr. Ram, and all. It was interactive and good lectures are there with interesting topics. So I hope student, Miss audience enjoyed much, and they learn about something, whatever talk is going on here. So, and I thankful for you people, especially Jana madam, and so he invited me for lecture, and yeah, it's okay. Thank you very much for.
Thank you, sir.
Thank you so much, sir. Thank you so much, sir, for your speech, for your lecture, sir. Thank you so much, sir. So now let's go to the attendees or participants. I have Dr. Ansu here. I didn't see her face, so maybe she's my friend. Let unmute her first. Let's see, Dr. Ansu, are you there? Hello, Dr. Ansu?
Yes, sir.
Yeah. Hello.
Good afternoon, sir.
Hello, good afternoon. How are you?
I'm fine.
Fine, yeah.
Your webinar was excellent.
Yeah. Thank you, Dr. Ansu, for attending the webinar. Thank you so much. Hello, Dr. Ansu. Hello. I think there is some connectivity issue with Dr. Ansu. So let's move on. We have a participants from Jain College, Nancy Borang. She want to share something. She want to share the experience of this webinar. So hello, Nancy. Hello, Nancy. Hello. You can talk now.
Sir.
Please, अपना experience share कीजिए. Share your experience.
Okay. Good afternoon, all. First of all, sir, I would like to express my gratitude to all the faculty members who had organized such a splendid webinar in this current pandemic situation. The webinar was such a helpful platform to motivate the youthful mind to think out of the box by incorporating various topics of physics like beauty of quantum mechanics, nanotechnology, etc., which was a high energy jump to boost the young minds of Northeast India. I would also like to praise the teachers, like the presentation style of all the informative teachers engaged were marvelous, dynamic, and educational, facilitating a terrific topic discussion, bringing all the insights of the principal topics. Finally, I thank the principal of this college, organizers, and all the teachers once again for bringing whole new level of educational and professionalism. Thank you also.
Okay, thank you, Nancy Borang. I request the participant to raise the hand if you want to interact.
I would like to request Biswajit Pal from Rajiv Gandhi University, Department of Physics. Biswajit, can you hear me?
Yes, ma'am, I can hear you.
Okay. Can you share your experience?
Sure, ma'am. Good afternoon to all. I am Biswajit Pal, an MSc Physics final semester student from Rajiv Gandhi University, Arunachal Pradesh. Thank you for allowing me to say something. Well, I would say that this 3 days long national webinar is highly successful. See, because in this lockdown, every institution is organizing many webinars. But being a physics student, I always try to find the lectures which will be based on the topics related to like UG or PG course in a very lucid manner, so that it can help me to understand the topics which I have already read, and which can help me to choose a topic on which I can pursue my further studies. And genuinely, this webinar helped me a lot to understand and to find a new way which I didn't think before, like Saurabh sir's quantum mechanics, Anup sir's nanotechnology, Saria sir's plasma physics, and beautifully Pratap sir's string theory and Noimuddin sir's neutrinos. All lectures are very good. Awasthi sir's alphabet and grammar of nature, and lastly Gupta sir's talks. All topics are covered in a very simplified manner, which will surely help all UG and PG students. And I have only one request to the organizing team, that ma'am and sir, please make available all the PPT and videos in the dedicated Gmail and YouTube channel so that we can see it again and again. It will help us a lot. Thank you so much to the organizing team. Thank you so much to my teachers. Thank you so much to the Department of Physics, JNC College, Pasigat. Thank you.
Thank you, Viswajit. Now I would like to call upon Jonan Rosang from JNC College, Pasigat. Jonan, can you hear me? Hello, Jonan.
Hello.
Yes, Jonan, we can hear you. Can you hear your experience?
Yes, ma'am, sure. Yeah, thank you so much, ma'am, first of all, for the opportunity that's been given to me. First of all, good afternoon and warm salutation, first of all, to our esteemed speakers and resource persons, sirs, our HOD ma'am, Dr. Jenti, and all our respected coordinators, and also to all the participants. Today, as we come on third and final day of our national webinar series 2020, where the theme is Advancement and Innovations in Modern Physics. Hi, Jonan Nonrang, and UG student from Jawaharlal Nehru College, Pasigat. I'm privileged really enough to be speaking here in front of all our respected resource persons, speakers from all around the country, who gave their precious time for our students and also shared their valuable wisdom to us. We are so much thankful for the topics our respected speakers explain us with, like quantum physics, plasma physics, and nanotechnology, neutrinos, string theory, etc. As all were very important topics to be discussed on. We were excited, to be frank. I myself was also really excited to learn something new and innovative and in detail. And indeed, our expectation and waiting was worth it. So thank you so much to all our esteemed resource persons and speakers for making of this year's national webinar a successful program. We indeed learned something and benefactory. And also, I would like to give my hearty thanks to our respected principal sir and organizers, our sirs and madams of the Department of Physics, Jawaharlal Nehru College, Pasigat, for giving us this wonderful of an opportunity to learn and discuss on important topics. I, as a learning student, would really express my heartfelt thanks to all and for organizing and making it indeed a successful program. I'm sure that all the ideas we achieve during 3 days of learning will be of great value in our further studies. And I really hope that it will be organized again in next year, and it will be so much good if it is organized. So thank you so much. I'll conclude here. Thank you once again.
Thank you, Jonan. Now I request any participant which wanted to share.
We have Sarah Lego, Miss Sarah Lego. He is assistant professor in Indira Gandhi College, Teju. Sarah. Hello, Sarah.
Let me unmute her.
Hello. Sarah, are you there? I think she's not here.
She's muted. Ask her to unmute. I'm unable to do. Yes. Yeah.
Hello.
Now we can hear. Hello, Sarah.
Hello.
Share your experience, Sarah.
Hello.
Yes, we can hear you.
We can hear you.
Actually, I have some network issue. Hello.
Okay. It's clear.
Hello.
Yes, Sarah, madam, we can hear you. We can clearly hear you.
Oh, okay. So it was great attending the webinar. Like the talks and the speaker, like they share the topics that they cover were also quite interesting, and it was a great experience for me.
Okay. Short and sweet. Thank you, Sarah.
Thank you, Sarah Madam.
If anybody,
Okay, thank you so much.
any participant want to share the experience, can raise their hand. It's Deepak Chauhan. So, share his experience. Let him allow to talk. Deepak?
Yeah, everyone.
Yes.
Hello, sir.
Okay.
Hello.
Hello. Yeah. We can hear you.
Yeah, am I audible, sir? Yeah. And I was your student, sir. Even sir, taught during my sir. Now I am pursuing a PhD in high physics.
Okay.
Sir, if future, sir, if incorporate with some key topics.
Okay.
So, sir.
Okay. I think there is a network issue. So there is one Wahidur Rahman want to share his experience. That's okay.
Hello, sir. Hello, ma'am.
Yeah.
It
Please.
was a
share
great.
your experience.
It was a great experience. Thank you for organizing such lovely webinars. Thank you very much. And I would like to make a request. Can you please send us the mail address of Dr. Pramod Gupta, sir, so that
Okay.
Sure.
we can reach him up.
Okay.
Thank you very much again for lovely talks. Thank you.
Okay. Now we have Lojar Rebi. You want to also? Okay, Lojar, you can share your experience.
Thank you, sir, for granting me such a great opportunity to speak in this platform. So, firstly, my hearty namaskar to everyone present here. Firstly, my name is Lojar Ravi Kojum, and I'm pursuing BSc Physics in JNC College, Pasigat. So, firstly, I thank the organizer committee to conduct such a great and valuable webinar. I think such webinar and knowledge sharing sessions held frequently. And secondly, I thank the highly knowledgeable and dedicated speakers. They did such a great work, make such a hard topic that was and understandable to us in very nice and easy way. Even at some places, the network was not proper, but they did still very great to make us understand and deliver what they wanted to. So, like example, yesterday I still remember that Dr. MD Naimuddin sir, he was changing places. That was a very hard for him, but he did his best to make us understand. So at last, I want to say that I hope that in future there should not be any network problems, and overall the session was excellent and great. I feel throughout the session I felt most enlightened.
Okay.
Thank you.
Thank you, Loza. So now I would like to put the webinar report. So I'm very happy to give this report, and it's a very positive sign for us as a coordinator. It's the first webinar organized by me and Dr. Yana here in Jawaharlal Nehru College, representing the Department of Physics. So total participants that has registered was 375. Among them, 70% were students, 10% were research scholars, 10% were faculties, and 10% were some others from others category. And from all India, 164 institute represented in this webinar as a panelist or as a attendees. So it's a great achievement, I feel. It's a 164 institute or organization has give their representation here in webinar. And we were lucky, we were blessed to have 7 eminent speakers across the India and across the globe also. We have promos from the South Korea also. So they were Dr. Kamal Saharia from Neres, Dr. Anup Kumar Nath from Cotton University, Dr. Pratap Kumar Soin from NIT Arunachal Pradesh, Dr. Muhammad Naimuddin sir from University of Delhi, Dr. Ramlal Avanti from University of Delhi, Dr. Saurabh Bhattacharya from Tinsukia College, and Dr. Pramod Kumar Gupta from way from South Korea. So these were our 7 eminent speakers. In the first day, there were 172 attendees. In second days, there were 177 attendees. And in third day, we reached 205 attendees. So it was a in term of attendees also, it was a success. And in term of our organization, or in term of organizing this this webinar, it was also a success. Speaker were having no problem. There were some glitches, but it's happened in the online webinar or online seminar. So overall, I feel we have been successful. And dear participants, there will be a overall feedback, which is mandatory for all the participants to fill up the form. So the feedback form will reach your that's a registered email and a WhatsApp group by 5 o'clock this evening. So please fill up it, and we'll give 2 days for that. Okay, and the certificate, e-certificate, the participation certificate will be given to you via registered email under 14 days from completion of the webinar. So thank you so much. So now I request my coordinator, our coordinator, Dr. Yana, to give the vote of thanks of the valedictory function. Thank you.
Thank you so much, Dr. Inuklivang. It has been our pleasure to host all the participants in the 3 days National Webinar Lecture Series, Advancement and Innovation of Modern Physics, conducted by Department of Physics, Jawaharlal Nehru College, Pasigat, Arunachal Pradesh, India. I give my heartfelt thanks to all the participants to attend this 3 days National Webinar Series. And we have been fortunate to have some of the eminent speakers from across the nation. I'm sure that the participant must have identified by benefiting by attending this webinar. I'm very thankful to Dr. Milorai Modi, the principal of Jawaharlal Nehru College, Pasigat, for his inspiring mentorship. I'm also very much thankful to Dr. D.P. Fanda, IQAC coordinator, Jain College, Pasigat, for all the generous support. It would not have been possible to organize this webinar without his support. I'm sure that IQAC will continue to provide generous support in future also. I'm very much thankful to Dr. Fadi sir, coordinator UGC NAC JNC Pasigat, for his valuable supports and motivations. I'm also very thankful to all the JNC administrations in general for providing us with all possible logistic supports towards organizing this event. I'm also very much thankful to all the eminent speakers across the nation, Dr. Anup Kumar Nath from Cotton University, Dr. Saurabh Bhattacharya from Tinsukia College, Dr. Kamal Saharia from Department of Physics, Neris, Dr. Naimuddin from Department of Physics and Astrophysics, University of Delhi, Dr. Pratap Swain from Department of Physics, NIT Arunachal Pradesh, Dr. Ram Avasti from Venkataria College, University of Delhi, Dr. Pramod Kumar Gupta from Hanyang University, South Korea, for accepting our invitation as a resource person. I'm also very much thankful to Professor Sanjeev Kumar, Head of the Department Physics, Rajiv Gandhi University for accepting our invitation as keynote speaker and integrate our program by his graceful speech. I thank all the plenary speakers and the keynote speaker for their enthusiastic participation in this webinar. I also acknowledge the unwavering support received from the head of the department, Dr. S. Jainty, and the faculty and staff members, Mr. Pakchim Yongam sir, Mr. Dutam sir, Mr. Manish sir. I'm also very thankful to Yaga madam, the staff from our department, for providing us delicious snack and tea. I'm also very much thankful to Dekada, our college canteen owner, for providing us wonderful lunch. I'm very much thankful to all the participants, and we are so happy. We have a lot of registered participants across the nation. And once again, I'm thankful to our eminent speaker across the nation. Thank you very much. We hope that in near future also we will conduct another extended webinars for students, for scholars, and for faculties. We may have some lack of internet issues since we are conducting from Arunachal Pradesh, and this is the month we have a heavy rainfall in Arunachal Pradesh, so we have a lot of internet connectivity issues, but the God grace, the internet issue was fine from host sites and from speaker sites. So for that also I'm very thankful, and thank you so much for bearing our problems. Thank you so much, all the participants, and we hope to see you again in hopefully in our next webinar. Thank you so much. With this, I'll conclude this validatory program. Thank you so much. Thank you so much.
Now everybody can leave. Everybody can leave.